And I also wanted to talk a little bit about the final. Final will most likely be in class. It will have a bunch of questions. 50% of the questions will be straight out of homework, not even changed. So go look at your homework problems, okay? Look at the solutions. 25% of the problems will be things that I mentioned in class. Pay attention, I might ask you. Anyone remembers any of those? Which one? No, no one remembers? Go ahead. Internal pressure, what were you saying? Oh, good. So there might be things like, yeah, go ahead. Yeah, things like those. So if you have paid attention, you wouldn't have any trouble. They will be easy. If you have not paid attention, you might be like, what the hell is he talking about here? You know. So I will be like, prove chemical potential and partial molar type things. Remember, there will be 25% problems which you would not have seen. And that's going to distinguish the A plus from the A and the A minus. Otherwise, I'm quite lenient in grading. You will have to make it hard for me to not give you a good grade. Some of you have already managed that, and I can't help it. So please don't try to make it hard to. Please help me help you, okay? Okay, so, and pay attention, because today we are going to have a pop quiz. I never said that. So what are we talking about? Last time, today we are going to talk about two things. We are going to talk about the lever rule. And after that, we are going to talk about real solutions and activity, okay? These are the two topics we will cover today. Both are short, but they are important. And once we do that, after Thanksgiving, we will do equilibrium constant for 2 classes roughly. Then 1 class, you are all making a presentation. So this will be around 2 classes. 1 class is presentation. And then I'm going to cover something related to chemical kinetics for 2 classes. This will be not on exam. The final part will not be on exam. And I will tell you when I'm going to cover it. If you really don't care to learn, please don't come, that's okay. But if you do want to learn, this is something books don't talk about. This is very important because guess what's missing in thermodynamics? Dynamics, right? There is no time. It tells you something will happen, but doesn't tell you when. So it's important to get a perspective of kinetics. And we will do that. It won't be on the exam because it is so close to the final part. In the feedback that I took mid-course, one of you protested, only one, which I'm happy to see. There are too many problems in the homework. But I think that's for a reason, right? To help you practice through it. There are many professors who don't give homework. And trust me, that sucks more. You don't learn. So kinetics will not be an exam. I do hope you come to the class and appreciate the topic because there is not much of an opportunity to learn kinetics. Here we will talk about rate laws and fixed laws of diffusion. We will talk about something called the Drunk-Gamler problem, which is super cool. And after that, we will have 1 or maybe 2 class, depending on how much time we have left to do recap of the whole semester, okay? So we will finish around 9th or 10th December, something like that will be the last class. You know, there is a week after that, we will probably not have. This is all tentative, okay? So don't take me to court on this. This is the tentative plan. Any questions? Okay, so let's talk about lever rule. Why do we need this lever rule? So if you remember last time, we were talking about how free energy curves move as a function of temperature, right? So last time we saw that at very, very high temperature, the free energy of vapor phase is much lower than free energy of liquid, right? And as we go to very low temperature, at very low temperature, it flips completely. The liquid becomes more stable than vapor. And in intermediate temperature, we had these funky things where the curves could cross. At intermediate temperature, we had things such as the curves could cross. One of them could be liquid, One of them could be solid. Maybe last time I flipped it around. I think Noah pointed out to me that I flipped it around, but doesn't matter. Depends on which phase is on the left side. This could change. But the whole point here was that in the middle region, something interesting happens. In the middle region, and let's really zoom in up here. If you have a point over here, clearly the free energy, why did I write solid? My bad. It's vapor. We are talking about liquid and vapor. It could apply to solid also. There is nothing. It could apply to any two generic phases. So the point here was that at this temperature, clearly liquid has a lower free energy than the vapor, right? The black is below the red. But is that the lowest free energy the system can have as a whole? So if the system stayed here, what would matter is that the system takes this concentration, X1, right? But if it drops down to here and inset splits into a combination of two other concentrations, so here we are talking about XB. If this becomes a combination of two other concentrations, it becomes liquid with concentration XL, and it becomes vapor with concentration XV. You can see that the free energy has gone down, right? But why would two phases ever coexist? Why can't we always do it? We can do it. Why can't we do it for, and this is the strange thing about this Maxwell common tangent construction. Once you split this, it's really important to consider this common tangent line, because the common tangent line says that the slope of the liquid curve over here is the same as the slope of the vapor curve over there, right? So these two phases can exist in equilibrium. So so think about it physically. It's almost that you could have been liquid, but instead of that, you decide to separate into two phases. You separate into another liquid and a new vapor phase. The another liquid that you have has lower concentration than what you would have had if you were all liquid, but the vapor that you form has slightly higher concentration that you have if you were all liquid, right? So you have separated into two concentrations. The most important thing to keep in mind is that the concentrations that you split into do not depend on which part are you in between these two. And this is kind of intriguing, right? And as we will see in a moment in the phase diagram, this is super important. Anytime, so let's go and look at it at the phase diagram and what it means. Okay, so this is just a recap. I'm gonna go to the next screen. So if we draw a phase diagram, which we drew last time, we had our temperature over here. And here we are going to talk about concentration of B. And then we had some two-phase region. Okay, so this one was liquid. This one was vapor. And in between, we have liquid plus vapor. So let's imagine you are at a certain temperature T, okay? And we move along this line. We are going to move along this line. So let's work through it carefully. Let's say we are at point 0. At point 0, so this is XB is equal to 0. This is XB is equal to 1. At point 0, is this system going to be liquid, vapor, or both? Go ahead. Why? It's in the liquid part of the phase diagram, right? Is that clear to everyone? At point 4, what it's going to be? What do you think? No, in front of you. I forgot your name. Yeah? At point 4, is it going to be liquid or vapor or both? Point 4 being here. Think once again. This is the part where it will be both. The only part in the middle. So the part to the, yeah, not the line, but the point 4, right? You're correct that on the line, it can be both. You're absolutely correct. Great, thanks. Sorry for putting you in for. So as we move from point 0 to point 4, it changes completely from liquid to vapor, okay? The question is what happens here at point 1? At point 1, it is still liquid, right? So this is an experiment where, I don't know, it's water or sugar, for example, and you are keeping the same temperature and you are increasing the amount of sugar. you're adding more and more sugar. So until you reach a certain mole fraction of sugar, let's say X1 mole fraction of sugar, you are going to be entirely liquid. That makes sense, right? Sugar keeps dissolving. But once you add too much sugar, something interesting is going to happen, right? Once you add too much sugar, what happens? You still have a sugar solution, which is very sweet, but you will start seeing crystals of sugar. Make sense? Right? This is something we have all done at some point. So at this point, in this case, this is not liquid and solid, this is liquid plus vapor, but the same ideas apply. So at this point, you will see the first appearance of the other phase being vapor. What will be the concentration of this other phase? It will be this point. And that's the funny thing that we saw from the common tangent construction rule. So the first time this other phase appears, it will have concentration X is equal to X2, even though you are here. So at point 1, all liquid. As we go to right of point 1, we will have liquid with XB mole fraction X1 and vapor with XB mole fraction X2 as we move to the point of right 1. And the interesting thing is that the mole fractions of the liquid and the vapor that you form are always going to be the same. So this is very intriguing. This is telling you that as you start adding more and more sugar to your solution, the water that you have seeing will always be the same amount of sugariness. It's not going to become any more sugary. And the solid that you're going to see in the bottom will always it's also going to have a bit of water, right? It will always have the same amount of sugar. The concentrations won't change. What will change? The relative quantities will change, right? You will have different number of moles of liquid and different number of moles of vapor in this case. So let's try to make a table for this. So this is, we did point 4 already. Let's call this point 2 and let's call this point 3, okay? Let's make a table. And in this table, let's call it point number. Let's talk about the number of moles of liquid we are going to have, number of moles of vapor we are going to have. And I want to talk about one more thing, which is, the notation is going to look a bit strange. It is small l subscript L. It means the length, the distance you have moved from point L, okay? And this one over here is small l subscript V, okay? And we are going to work with all this. So the relation we are going to prove, Liver rule says that NL, the number of moles of liquid by number of moles of vapor, is equal to this length vapor divided by this length liquid. This is Liver rule that we are trying to prove. And let's try to get intuition into it. It's super, super useful for any two phases. And here we will talk about LL, and here we will talk about LV. So point 1, 2, 3, 4. At point 1, how many moles of liquid do we have? Someone who has not answered. You three have answered, so someone else. Alex, what do you think? Number of moles of liquid at point 1. Yeah? Let's say total number of moles is N. You need that information. At point 1, do you have any vapor? No. So what's going to be NV? 0. So what's going to be NL? N. Right? Alex nailed it. Thanks, Alex. I hope you were not up all night. Put you in a shock condition. Sorry. Okay, point 2. Who wants to help me with point 2? No, actually, let's go to point 4 first. Yeah, go ahead. And NV? How about point 3? How about you only help me with point 3 too? Also. Is point 3 really any different from 4 in terms of liquid and vapor? No, it's the same. Do you agree, Corina? Good. So 0.3 is still 0 and n, right? So 0.2 is the complicated point. That's where we need to figure out. At 0.2, what would you expect NL to be? It will be somewhere between all liquid and no liquid, right? So it will be some number between n and 0, right? Maybe it will be n by 2. Maybe it will be n by 3, depends on where you are, right? So this is what we need to figure out. And my claim is that you can calculate this by going to the phase diagram, taking a ruler or a scale, and just measuring these two lengths. If you can measure these two lengths, that gives you the ratio of NL by NV. If you know the ratio of NL by NV, you also know the sum of NL plus NL and NV. The sum of NL and NV is N, right? Two variable, two equations. You can solve it and calculate the number of the moles you will have of liquid and vapor, okay? So let's work through this. Let's try to prove this. So in order to prove this, and really the proof is important, but what's more important is to remember the relation. You get a feel for what it is because it's really, really useful. You have to calculate, and it kind of makes sense, right? Because let's see if it makes sense. What is the value of LL at 0.1? What is the length from 0.1 that you have covered in order to get to 0.1? 0. You're just sitting there, you haven't moved. It's like, what is the distance between me and me? 0, right? What is LV at 0.3? 0, right? You have moved no distance from the vapor. So this is 0. So you can now go and see in this case, and this thing will be something else we have to calculate. That is the full length of the, by the way, this line that I drew here is called a tie line. Okay, that's the name for this line. It's called a tie line. So if you're moving along the tie line, you can go and see here, if you do NL by NV now, it will be how much? N by 0, which is infinity, right? And what will be LV by LL? That will be LV, whatever value it is, divided by 0. So both agree, both are infinity. If you go to this one over here, what is NL by NV? NL by NV is 0 by N. And what is LV by LL? It is 0 by LV. Again, both are 0. They both agree. So it makes sense at both ends. You cannot really do it outside the tie line, right? Because then the length becomes negative and it does not help us. There, you don't need to use Lever rule anyway. You know there is only one phase. You know the mole fraction of that phase. So for the proof, let's calculate number of B moles. So we have a two-phase system with A and B, components existing in two phases, liquid and vapor. So at 0.2, let's calculate the number of moles of B in two different ways. And let's equate it, and that will give us the Lever rule. So how can we calculate the number of moles of B at 0.2? Any ideas? Go ahead. Perfect. So what is the total number of moles? N. And let's say the X value here is XB. So N multiplied by XB. So Daniel is correct. This is N multiplied by XB. We can do one more thing. We can say N is equal to NV plus NL. So we have NV plus NL multiplied by XB, right? This is one way of calculating it. Is there another way of calculating it? And this is slightly harder. Daniel was smart. He got the easier way. There is another harder way. Go ahead, Ryan.
Nx2.
Give me the intuition, not the algebra.
It's the amount of liquid times the mole fraction of the liquid plus the amount of the volume times the mole fraction.
So what Ryan is saying is that at 0.2, you know the total number of moles. You forget that you're split into two moves. That's what we did first, right? We just completely ignored that we have two different phases. We looked at total number of moles and we multiplied it with the full mole fraction. But where is B coming from? Some of it is coming from liquid. Some of it is coming from vapor, right? The part that is coming from liquid has how much B? that is number of moles of vapor multiplied by mole fraction at that point, which is x1. And why do we know that the part coming from liquid will always have mole fraction x1? That is the common tangent construction that showed us, right? It will only split into those two. Plus NL multiplied by x2. And this numbering might be a bit confusing because I called it 0.3, but hopefully it's not too bad. So now we can equate both of these, right? So we can equate both of these. What will we get? We will get NV multiplied by XB plus NL multiplied by XB is equal to NV multiplied by X1 plus NL multiplied by X2. Therefore, NV multiplied by XB minus X1 is equal to NL multiplied by X2 minus XB. What is XB minus X1? That is LL, right? That is the length of that thing. Therefore, NV multiplied by LL is equal to NL multiplied by LV. And we have proven our Lever rule. So if you forget the proof, that's okay, but remember the relation. It's super useful. Either on the next homework or on the final, you'll probably have some problems on this. I will draw you some phase diagram, and I will ask you to calculate what is the mole fraction. I will ask you two things. I will ask you what is the mole fraction of the phase that appears. For that, if you know the common tangent rule, it's very simple. The full mole, the concentration in the phase that appears is always given by the end of the tie line, right? It doesn't matter where you are along the tie line. The concentration of this phase is going to be over here. And the concentration of phase liquid is always on this point. The concentration of phase vapor is always on the right side. What changes is the relative mole fractions. And that you can calculate through Lever rule. Go ahead. XB NL did I derive the opposite thing? That would be terrible. Let's see if it makes sense. Yeah, it should be NVLV. So I did something stupid. NVXB plus NLXB. Yeah, it should be NVX2. This is correct. So we are talking about vapor, right? This point, that has mole fraction X2. Sorry about that. Yeah, so I said the right thing, but wrote the wrong thing. So the number of moles of vapor, which is NV, multiplied by the mole fraction of B at that point, which is coming from X2. And this mistake happened because I have called it 3 over here and 2 over here, which is terrible of me. So therefore, NV multiplied by X2 minus XB is equal to NL multiplied by XB minus X1, or NV LV is equal to NL LL. Now it's also easier to remember. You have the same terms on the same side, right? Number of moles of vapor multiplied by the length from the vapor point, which is LV, is equal to number of moles of liquid multiplied by length from the liquid point. Any questions about this? Okay. Time for a pop quiz. Again, you're not going to be graded on this. Try to do an honest job. Just because you know you're not going to be graded, don't write goofy answers. Let's do a good job. Let's talk about. The first problem, don't discuss. The first one is plus R. There's no T. Okay. Everyone, can you pass it to the right, to your right? And keep passing, so I will go from this side and collect some. Okay. Okay, what we're going to do is collect on the right and come and bring it up there. One person who is sitting in the right mode should collect and bring it to the left. Just leave it here. Okay, everyone done? All right. See a bunch of wrong answers for A, for the first one. There were two answers which were false. One of them is obviously false. Which one is super obviously false? Yeah, clever, huh? Sneaky. Don't worry, you're not being graded. This is life without judgment. Huh? It's awesome. Now, does it make sense? So who said you? What's your name? Yeah. So you said you got it wrong because it was.
Because I thought it said which one is true.
You want to try now in front of us?
In front of you, I believe A and C are false.
Why is A false?
I mean, obviously, S is both positive.
Yeah, but also, yeah, A, you did get it right. You can just rule it to be wrong simply by looking at the sign of S, but A was doubly wrong because enthalpy of mixing cannot be. Ideal mixture is the enthalpy of mixing, right? Mm-hmm. So don't worry, I won't try to do tricks like this in the final exam. The questions will be simple, okay? There won't be any, I don't like to soft pulls of trickery like this. How about the second one? We studied an equation for this. Anyone remembers the name? Clapeyron equation, right? So I would have preferred, I really gave you the hint, dg is equal to vdp minus s dt. So I would have preferred delta s by delta v. Some of you wrote delta h by t delta v, and that's also okay. There is nothing wrong with it, okay? So delta s by delta v is the, so in this one, this is wrong, this is wrong, this is correct. And then here I would have written delta s by delta v, but we know delta s dq is equal to tds. We saw that this is equal to dq by t for a reversible process. So if you wrote it as delta h by t delta v, as some of you did, that's also okay. It's not g. Please check your dimensionality. If you have any question, you can do any level of science. Dimensionality check, dimensionality consistency should be a first test. Always check whether the answer you wrote makes dimensionally any sense or not. Any questions about this? Okay, good. Pop quizzes are fun, right? They're more fun when I have to give them. It's not as much fun taking them, I'm sure. It's not too bad. Okay. So, okay. This is a good segue into the final topic before Thanksgiving, which is just a little bit about real solutions and this concept of activity. We'll just do a little bit. I might start with this topic when we come back after Thanksgiving, just to refresh your memories. But I'm going to start it today. We might not finish it, and that's okay. We will resume whatever we are doing from now. I will resume from here next time. Okay. So we wrote that delta mixing H is equal to 0 and delta mixing S is equal to, what's the sign? Even I forget. The best way to remember is to look that its entropy of mixing should be always positive. And if you look at this one, this is always negative, right? So minus R xi ln xi. This was true for ideal mixing, right? Then we talked about real mixing in irregular solutions. In regular solutions, which we found are actually quite useful for understanding a variety of things. I did not go into more details from regular solutions because we didn't have time. So there we found that we did not find this is one of you asked me, why do you have this for a regular solution? There is no why. This is how we describe our model, right? Why is the atomic model made up of atoms? It's a model, right? It's made up of atoms. You could have a pasta model made up of pasta, right? It's the model. Some of you might have heard about the flying spaghetti monster. Has anyone heard of it? It's the god of Pastafarianism, right? I think it's a pretty awesome religion. So for regular solution, we said delta mixing H is going to be omega multiplied by mole fraction of A multiplied by mole fraction of B. So if you set omega is equal to 0, you recover the ideal model, and delta mixing S is going to be the same. So turns out regular solution is quite useful. Even ideal solution is kind of useful. The nice thing about ideal solution is this entropy term that we had over here, right? Which is super powerful. And it's so powerful that we kept it in the regular model. Real solutions might deviate from both, right? Real solutions delta mixing H might be something completely different from omega XA, XB, right? You might not be able to fit it to XA and XB. And delta mixing S might be also completely different from the thing that we wrote above. So how do we deal with all this? There are many ways of dealing with this. One way of, so this would be real model. So one way of dealing with this delta mixing S is to go beyond, and this is purely, this is out of syllabus. Okay, I'm not going to grill you on this, but some of you might like to read. So we have to go beyond a pair approximation. So what this means is, if you go and read how a regular solution is really derived in what is called the quasi-chemical model, which also gave us a value for the omega, right? We showed omega is equal to, I wrote for you that omega is equal to epsilon AB minus epsilon AA plus epsilon BB by 2, something like that, right? So there is a quasi-chemical model, which is a pair approximation. It always looks at two things, entropy due to pair of things at the same time, right? So there are more complicated models that go beyond it. They are called models such as cluster variation models, which allow you to go beyond pair approximations, and they can correct the entropy in a very, very significant way. So I mentioned this because this cluster variation method came in 1950s from someone named Kikuchi. If you go and look up that paper, it's a paper full of algebra, and you're like, who's gonna use it ever? So when I was a sophomore, my first research paper was on using this. It was a lot of fun, but type 3 fun, it was just terrible. It's just terrible, terrible algebra. I had like Mathematica and Maple, and I went crazy. I think it contributed to my hair loss. It was so terrible. Turns out, in modern day AI, people are using these same things to think about entropy. So all these methods that were in chemistry in 1950s are used in AI to understand how people talk to each other. You have a social network, right? You have your Facebook, you have your Instagram, you have your Pinterest, whatever, your TikTok, and you want to model it. How does your reaction influence someone else's reaction? How do you arrange different reactions? And these models from chemistry are being used to understand those things. So it's super cool. We are not going to talk about all that. It's complicated. If you take graduate statistical mechanics, you might talk about that a little bit. But we are going to think about this problem in a more general way. Okay, we are going to think about the problem from a more experimental perspective. And that leads us to the concept of activity. So I'm going to stop here. I will start with activity next time. I want you to think about a relation. And this is the relation I will derive. We kind of saw it earlier, but we skipped it just a little bit. So I want you to think of this as a practice problem. Atkins does it carefully. So go and look it up. This will help you after the exam, after the Thanksgiving break. So I want you to derive the following relation, that ideal mixture of A and B, the chemical potential of A goes as mu A naught plus RT ln XA, and chemical potential of B goes as mu B naught plus RT ln XB. So I want you to derive this. This is practice problem 15 or 16, I don't know what it is. This is done in Atkins. Think about it, how this is done. We will start from here. We will talk about activity next time. Then we will talk about equilibrium constants. And that is the last topic which will be on the exam. Once we finish equilibrium constants, whatever time we have left, we will do a little bit of kinetics, which will not be on the exam, but I hope you still come and attend. I will tell you when we go beyond the exam stuff, I will tell you, you don't have to attend. And finally, we will do a recap of the whole semester. And your midterm, the report is due in class on next Monday. And you should send your presentation as a team to me on Slack or email by Tuesday night.